All right. What we want to do today is we want to practice with two-dimensional kinematics problems. We're going to do first, we're going to break everything up into components if it's not already in component form. Then we're going to do kinematics with the x direction, and we're going to do kinematics with the y direction, and we're going to keep them separate. There'll be some link between them that tells us what we care about. So, third will be find whatever links them. To solve our problem. So, suppose that I had a table. We're going to start with a real simple situation. And I had a ball and it rolled off the table. And suppose we have a ball rolls off a 0.80 meter tall table. The ball is going 2.4 meters per second. And I would like to know, where does it land? Well, it's going to go off the table and it's going to arc down and hit someplace on the ground. And so what I want to know is, how far out from the table is it when it lands? I don't want the answer on the floor. We know that already. We want to know where on the floor. So we're going to look at this. We're going to set up x and y components. In this case, I'm going to put x going across and y going up. And I'm going to make my list of things that I know and things that I don't know in the x direction and in the y direction. And as I do this, I'm going to have to put everything into components. So I think I'll make my list this time. Delta R, V naught, V, A, and T. And I'll put the x component here and the y component here. Now, after the ball leaves the table, it's in free fall. So free fall means my acceleration is what? 9.8 meters per second squared down. So I need to break this up into components. I need to have the x component and the y component. So I look at this, and x is across. My acceleration is down. How much of down is across? This is a trick question. How much, if I go down, how far east do I go? I don't go east, right? So if my acceleration is down, the x component is going to be 0. I'm not going in the x direction. What's the y component going to be? If none of it is in x, all of it must be in y, right? But we have to stop and think, positive y or negative y? Negative, because I look at my picture and I said y, positive y was up, so my y acceleration is going to be negative 9.8 meters per second squared. Notice that when we talk about free fall acceleration, we sometimes use the symbol little g. Little g is always positive. It's an amount. My acceleration might be positive or it might be negative. That will depend on which way I picked positive to be. Little g is always positive. A might be positive or might be negative. So I have my acceleration here. I'm going to say 0 in x and negative 9.8 meters per second squared in y. It's really 0 meters per second squared, but since it's 0, I don't really care. Then I need to look at what else I know. So, the ball rolls off a 0.8 meter tall table. So, I know its position is going to change from here to here. I don't know how far it's going across, so I'm going to put in a question mark for how far it goes across. But I do know how far it goes down. How far does it go down? It's going to go down 0.8 meters. So my change in position in the y direction, I'm going to go 0.8 meters. Positive or negative? Well, it's going down, and I picked up to be positive, so it's going to be negative 0.8 meters is my change in position in the y direction. Now, my initial velocity, I know, is going 2.4 meters per second. If I look in my picture, my initial velocity is going to the right. So, how much of that is down? None of it's down. So we're going to put in the 0 for v naught in the y direction. All of that is in the x direction, and it's all in the positive x direction. So I'll put in positive 2.4 meters per second in the x direction. Do I know the velocity as it gets to the floor? No. So I'll put in question marks there. Do I know the time when it reaches the floor? I don't know that either. Now, if I count up question marks, you will see I have 1, 2, 3, 4, 5 question marks. How many equations do we have? We have 2, right? Position equation and velocity equation. Except they have to be true for both x and for y, so that turns it into 4 equations. So I have 4 equations, and we get to solve 4 equations for 4 unknowns. But I have 5 question marks. how do I get rid of that fifth question mark? If I'm going to substitute, I need a fifth equation. And I don't have a fifth equation. I only have 4. But I notice time here, time is not a vector. The time when it hits the ground is the time when it hits the ground. These two times are the same. All my t's are the time it hits the ground. And that means I don't really have 5, well, I have 5 question marks, but it's only 4 unknowns. How do you feel about solving 4 equations for 4 unknowns? Happy? Not so happy. This is what you've been hoping you would get to do with all that math you had to take, right? It turns out most of the time that we don't actually have to solve all 4 equations. In this problem, it's going to turn out that we don't know the final velocity and we don't care about the final velocity, and so we won't bother to solve for those. We're not going to need it to get our answer. But we are going to have to do 2 equations and 2 unknowns. Now, if I look at my variables for the x direction, I notice I have 3 question marks. 3 question marks means I can't solve it. I can't solve for 3 unknowns with 2 equations. But if I look at my y data, I have only 2 question marks there. That means I could solve for both those question marks. That means I need to start with the y direction. So I'm going to look at the y direction. Now I notice that I know about the position, and so I'm going to start with my position equation. In the y direction, we will usually write it, change in y position is beginning velocity in the y direction times t plus 1/2 acceleration in the y direction times t squared. Makes it look a little fancier. You don't have to write it out this way, but you do have to keep the x and y separate. So, I plug in what I know. Delta y, negative 0.8 meters, equals v naught y, 0, times t, plus 1/2 times ay, negative 9.8 meters per second squared, times t squared. So 0 times t gives me nothing. So I have negative 0.8 meters is nothing, plus half of negative 9.8 gives me negative 4.9 meters per second squared, times t squared. So t squared is going to be 0.8 over 4.9. The meters will cancel out, and I'll be left with second squared. So t is going to be the square root of 0.8 over 4.9 seconds. And most of us will have to whip out a calculator for that. And I get 0.404 seconds. I probably will not want to keep 3 digits in my answer at the end. But I'm not at my answer at the end yet. If I keep an extra digit now, then any rounding stuff will go away when I throw out that last digit anyway. So it'll make it a little more likely that I'll get exactly the same answer as everybody else. So, now I know how long it takes to hit the ground. That time is now going to get carried over to here, because the time when it hits the ground is the time when it hits the ground. So now I'm going to look at the x direction. I want to know about the position, so I'm going to start with the position. And so I'm going to have delta x is v naught x times t plus a half ax times t squared. So I put in delta x. I don't know what that is, so I leave that delta x. Then I will have v naught x, that'll be 2.4 meters per second, times my time that I just found, 0.404 seconds, plus 1/2 times my acceleration, which in the x direction is 0, times my time, 0.404 seconds, squared. So this last piece goes away, and I'm left with delta x is 2.4 times 0.404, which gives me 0.97 meters. This one I'm rounding off at 2 digits, so it matches all my other stuff. And so this tells me the ball lands 0.97 meters away from the edge of the table. So this was kind of nice because we didn't have to solve anything simultaneously. We do our y direction, it gives us the time. We do our x direction using that time. We don't have any times when we're doing two unknowns in the same equation. Sometimes that comes up. Sometimes you have to do 2 unknowns in the same equation. Okay, so questions about this. At this point, if you're where I would like you to be, you should be able to follow along when I do this, and it should make sense. But when you go to do a problem all by yourself, you may run into difficulties. So, we're going to do that in a moment. Before we do that, because this reminded me, if you haven't looked yet, the quizzes that you turned in Monday night, they're graded, but also the solutions are posted. It's a Pencast posted in the discussion board on Blackboard. So you have some comments on your quiz about what went wrong, but also you may want to look at the Pencast of how I did it what tips you can pick up from there. Okay, so, oh, and another thing while I'm on the topic here, I learned yesterday that the latest Mac operating system broke video analysis on Logger Pro and a bunch of other stuff. So, if you're using a Mac and you had problems importing your video or getting things to work, there is a later version of Logger Pro that came out a couple months ago, and it fixes all that stuff. So, if you go to Vernier.com, and you can download the latest Logger Pro version. You just want to do the update. That will maybe fix it. I'm not going to guarantee. I don't have Mac, so I can't test it to see what the deal is. But I did find out that it broke some stuff, and there's a new patch for Logger Pro. Eventually I'll get that over into Blackboard, but that's not going to happen today. Yes? You bet. See, all I have to do is give you a little bit of time and you can come up with a question. Last thing about the Logger Pro update, though, if you're not running a Mac, I don't think it did anything. So don't bother to update. Okay, so if we come back up here to our Y stuff, we're using our Y position because we know what happens to the position in the Y direction. It goes down by 0.8 meters as we go from the top of the table to the floor. So our Y position change, that's our negative 0.8 meters. Negative because it's going down, and 0.8 meters because that's how far it goes. We start out not moving in the Y direction. We're only moving in the X direction as we go across the table. We haven't started to fall yet. So our Y velocity is going to be 0, and that makes the 0 times t term go away, and that's what means we don't have to use the quadratic formula. Then we have a half times our acceleration times our time squared. Our acceleration we know because nothing is holding the ball up after it rolls off the table, so we're in free fall, and we know that means negative 9.8 meters per second squared when down is negative. So we have our change in position, we have nothing from our initial velocity, we have a half our acceleration times our time squared. We want to get time squared by itself, so we divide both sides by 4.9, well, by negative 4.9, which makes the negative signs go away. Then we get 0.8 over 4.9. Divide that out and square root it. That's basically 0.8 over 5 gives us 0.16, and the square root of 0.16 is 0.4, so that's where we get our time from. And then we just use that time to find our X position. Better now?
Yeah.
Okay.
Is the negative 0.8 where the ball goes off from in the equation where it says 0.80 meters?
Right. So we're going from the top of the table to the table. So if the table is 0.8, we are going down 0.8 to get to the floor. So negative because we're going down, and 0.8 because of the table. And if we had said, let's let down be positive, which we could have done, then the 0.8 would be positive, and also the 9.8 would be positive. They're both down, so if down's positive, they'll both be positive. If up is positive, they'll both be negative. So, ready to try one yourself? So the way it usually works is I do an easy one, you try a harder one. We have a harder one for the quiz and the hardest one for the test, right? So let's make it a little bit harder. Because you want the hard ones to be on the test, don't you? I think that's what you're saying there. Suppose that my problem instead said, I throw a ball with an initial velocity of 5.0 meters per second up and 7.0 meters per second across. Notice I'm giving you the initial velocity already in component form. You catch it at the same height. As I throw it from. And I want to know how far apart are we? So, this one is going to be different because why? Why is this one going to be different from the one that I did? Now the ball starts out with an initial velocity in each direction. We're still looking for how far it goes. How far it goes is how far apart we are. But we have two velocity components in the beginning. So we're just adding one extra little piece in here. We still know the change in height. In the rolling off the table problem, we knew that the height dropped by 0.8 meters. In this case, what do we know about the change in height? It's going to be 0 because we're starting and stopping at the same height. So, take a moment, write out the change in position, the initial velocity, the final velocity, the acceleration, and the time variable list for each of the x and y components. I'm going to put it here. We'll have a space for it. Delta R, V naught, V, A, T. I'm going to run it sideways because I'm running out of room on my paper here. So do this for x and for y, and we'll talk after you have all of those written out. Make sure everybody's on the same page, and then go ahead and you can set up the problem and continue it yourself. So, if you're online, write them out for yourself, and then somebody be brave and post in the chat what you got. Or somebody post the x's and somebody else post the y's. Nope. It's not 7 meters per second. How do I know it's not 7 meters per second? Well, there's a trick to help us here, and that is we look at units. Delta R is going to be meters, or feet, or miles, or something like that. V and V naught, those are going to be in meters per second. Acceleration is going to be in meters per second squared, and time is going to be in seconds. So, we have 5 meters per second and 7 meters per second. Can those be changes in position? No. They have to be what? They have to be velocity. So they're going to come in someplace over here with our velocities. Our change in position is going to be in meters. Cody says, we don't know. And that's correct. We don't know. It's what we're looking for. Yes?
How does this everyone else answer that?
All right. So, delta R in the x direction is nothing. So, what were you going to tell us about what comes next?
Y, 0.
Y is going to be 0. Delta Y is 0 meters, and we know that because it says at the same height. So, what about our initial velocities? What's the x velocity in the beginning? Seven meters per second across. When we do this, when we've said our y is 0 and our v naught x is 7, we have said that across is the x direction. We haven't picked which is positive y, up or down. Anybody have a preference? Up. Okay, we'll pick up to be positive y. And across will be positive x. So, what's our initial velocity in the y direction? It's the 5.0 meters per second. What about our ending velocities? We don't know. And that is often the case. Often we will not know the ending velocities. And very often we will not care about the ending velocities. And so always in my heart of hearts I'm thinking, I hope I don't have to do anything with that. Okay, now our acceleration. What do we know about our acceleration? Y is going to be negative 9.8 meters per second squared. How do we know that? It's in free fall. It's not falling though. Right? I threw it. But we don't care. Free fall doesn't mean falling. It just means not being supported. So even though it's going up, it's still in free fall. So our acceleration in free fall is all in the y direction, which means how much in the x direction? Nothing. How long is it going to take? We don't know. So our time is question marks. But these are going to be the same time. So, how'd we do on that? If you got every one of those in the right spot, that's excellent. If you have one or two that are tripping you up, you know what to look for and to work on. If you had trouble getting most of them, then you'll want to be talking to me outside of class. So come to office hours or make an appointment to talk to me. While I'm thinking of it, I want to remind you that we have a Success Center. There are people there who are also available to help, both in person and online. They are not always all that great with physics, but they should be pretty good with kinematics, even if they're not physics people, because it's just math word problems. And they can help you out. They're quite good at algebra stuff. So if you're having algebra or trig issues, they can be very helpful. Physics stuff, find somebody who you can communicate well with, and you want to probably try and go back to the same person. Robert is usually pretty good. I don't know who else is over there, but find somebody who can explain it in a way that makes sense to you. All right? So, try and set these up and figure out how far apart we are. So, how we doing? Got an answer? If you got an answer, hopefully you got the right one. Our time here is 1.02 seconds. We get that from our position equation. 0 is 5 times t plus 1/2 times 9.8 times t squared. Then we use that time in our position equation, and that tells us that our change in x position is going to be 7.1 meters. So we are 7.1 meters apart. So if you got those, excellent. If not, see if you can work out what went wrong. Tomorrow, we're going to talk about how to measure mass in lab. We'll need that as we start talking about how mass affects things later on, starting next week. Friday, we're just practicing with kinematic stuff, 2 dimensions and 1 dimension, so we'll do some more examples and problems. Then next week, we have no class on Monday, that's Labor Day, and we've got our test coming up on Thursday, so I know that will make you all